Good afternoon, and welcome to SETI Talks at the Microsoft Research Campus here in Mountain View, California. Today, we're going to learn about geology at the edge of our solar system. Our speaker today has focused on a range of topics relating to the geologic evolution of planetary landscapes and crustal materials. He has published a number of papers on the geomorphology, stratigraphy, and sedimentology of, as well as explored the roles of impact cratering, volcanology, and tectonism on terrestrial planets and outer planet satellites. He has extensive space mission experience, which you can look up for yourself on the internet. I only have so many minutes here before his talk begins. His diverse background, which led him to his current position in space science, started with a bachelor's in history from the University of Oklahoma. From here, he earned his bachelor's in general geophysics and then his master's and doctorate in geology from Arizona State University. His first career was with the United States Army as a lieutenant, a tank platoon leader, and a battalion staff officer. His professional experience as a researcher started early on at the School of Geology and Geophysics at the University of Oklahoma and OU's National Severe Storms Laboratory, and then the Department of Geology at Arizona State University, which brought him to our own SETI Institute very briefly as a researcher, and he is now a research scientist at NASA Ames Research Center next door at Moffett Field, California. And he has been my friend and colleague for more than a decade. However, his role as the Geology and Geophysics Imaging Team Leader for the New Horizons mission to Pluto and beyond is what brings him to us today to talk about what we now know about geology after Pluto. Ladies and gentlemen, Dr. Jeff Moore.
Thanks, Ross. Can you all hear me? Is this picking up? It's working? Okay. The main reason I'm concerned about it not working is I think I have a good voice, which can be heard throughout the entire room, but they're also recording the show, so that was why it's important that I be heard. So I'm going to have to walk here and change my own slides from time to time, but if you'll indulge me. So that's the title slide. The only thing that you should walk away from the title slide is the fact that while I'm the speaker, there is a very large number of people, both engineers and scientists, that have made this all possible, of course. This involves hundreds of people, if not thousands of people, including the gentleman who just introduced me. Ross works with me on this mission, and everybody has contributed substantially. The things you'll see couldn't have been done without everybody else's contribution. There we go. Okay, so let's put things in context. So there are kind of three zones of the solar system. There's the inner solar system made up of the terrestrial planets, which we set on one. Beyond that are the four gas giants and their satellites, most of which are ice worlds. And then beyond the gas giants, there's sort of a third zone of the solar system, which is the Kuiper Belt, which contains, tens of thousands, if not a million objects down to some, arbitrary size. But it also has a collection of fairly substantial objects, of which Pluto is the largest, but you can see Eris is almost as big. Many of these small worlds or dwarf planets of the Kuiper Belt themselves have satellites. And as you'll see today, that Pluto certainly has its fair share of satellites. Pluto was discovered exactly 85 years ago this month by this gentleman, Clyde Tombaugh, who was an amateur astronomer, a self-taught individual who showed up at Lowell Observatory and was offered a job. And he didn't use this nice big telescope, but a telescope more like the size of this one he built to take photographic plates of the sky repeatedly, searching for a hypothesized planet X. And he indeed found just such an object moving in the sky. And after its orbit was confirmed, it was announced to be a planet, as I say, 85 years ago. Okay, so before New Horizons arrived at Pluto, what do we know about the place? Well, here are the best images taken of Pluto by Hubble, and people used a number of techniques to derive. By the way, no point in putting up your 3D glasses till the very end. I'll flash a sign, say, show your 3D glasses. There's little point in doing it unless you just enjoy doing it. I gave this talk a couple of weeks ago, and somebody put their glasses on at the very beginning of the talk and didn't take them off the whole time. I didn't have them urine analyzed or anything afterwards. It was all very fine. So as I said, a number of techniques were used to actually realize that Pluto did have quite a range of both brightness and and coloration. So we did know that Pluto would be probably a very interesting place to look at. But this is, again, the best we knew of it back before last year. We also discovered about 30 years ago, or I guess it's now 40 years ago, that it had one large satellite. It had Charon, or Charon is probably more properly pronounced Charon, but Jim Christie, who discovered it, his wife's name is Sharon, and he wanted to name it Sharon. So the compromise we have on the team is we mispronounce Charon as Charon, so that Jim would be happy about it. So you'll hear me go back and forth on whether it's Charon or Charon. Well, they right away discovered, that of course, the same sides of the two objects face each other. They're both in a day which lasts a little bit longer than 6 Earth days. And we right away determined that Charon is about half the size of Pluto. And just in the last decade, we've discovered that there are 4 more satellites of Pluto which are much, much smaller. So here's Pluto, here's Charon, and then these other satellites are really small. I'll show you, we did get some pictures of them, and so towards the end of the talk, I'll show you some examples of these images, but they're typically not more than a few tens of miles across at most, in contrast to Pluto, which is about the size of the Earth's moon, and Charon's about half that size. So some of the ideas people have had about how the Pluto satellite system formed this always seems to be everybody's explanation for everything, but it turns out when you try to model any other explanation, the other explanations simply really don't hold up. They're untenable as far as a dynamics perspective. So a lot of people have worked on this. Alan Stern, who runs the mission, Bill McKinney, who's a close colleague of mine, and Robin Knaut, who also works at Southwest Research Institute, which is where the science side of the house is run for New Horizons, all modeled this, and the explanation which best explains how Charon and the other satellites formed was from some primordial large impact event, not too dissimilar from how the Earth was formed, the Earth and Moon system was formed. We also knew from telescopic observations that the surface composition of Pluto is interesting, that it is dominated by nitrogen at a ratio almost 10 to 1. We also saw a significant contribution from methane and carbon monoxide, but we didn't see any evidence for water ice on Pluto, although we have seen evidence for water ice on Charon from spectroscopic observations, from telescopic observations. It also was discovered, getting back in the 1990s, maybe back to 1985 actually, that as Pluto passed in front of stars, known as stellar occultation, that it had a thin atmosphere. No one was quite sure how thick the atmosphere was. People speculated it might be around 10 microbars, which is 1/100,000th that of the atmospheric pressure of the Earth's surface. And it turns out this value is actually pretty close to what we also discovered. And I'll show you some of our results on the atmosphere here shortly. One thing I always like to remind people is that Pluto is primarily made of rock, not ice. We think of it as an icy world because it has an ice crust and has an upper ice mantle and may well have a liquid water layer sitting between the ice layer and the rocky interior, but by mass, most of the mass of Pluto is made of silicate rock. And because there is silicate rock making up the interior of Pluto, there's enough radiogenic material in there to contribute to some extent to radiogenic heating, and we'll see some evidence that maybe that's playing a role in modern Pluto shortly. Okay, so enough about what we knew before we launched the spacecraft. Just slightly more than 10 years ago, we launched the New Horizons spacecraft on the largest booster that was currently available to us at that time. These Atlas V's usually have in their cowling, a school bus-sized communication satellite to be launched in geosynchronous orbit, but instead we launched a thing about the size of a small grand piano in the very tip of the nose cone and traded mass for velocity. Everybody knows our momentum equation. So instead of putting something very heavy up in geosynchronous orbit, we launched something very light into a very fast trajectory. At the time it left Earth's orbit was the fastest thing ever to be launched from the Earth, from Earth's orbit. It traversed the orbit of the moon in about 10 hours, and put that in contrast, it took 3 days for the astronauts to get to the moon, and off we went. Oops. I thought there was I'm skipping something though. Okay, we'll just go ahead. So let's talk about the scientific payload. Now, most of the things I'm going to talk about are going to involve either the LORI, which is basically a black and white telephoto camera system, which will have taken our high-resolution images, or the 2 detector heads, which are in the RALPH instrument. The RALPH instrument is a combination of INVIC, which is our medium-resolution wide-angle color camera, and LISA, which is our imaging spectrometer. And I'll show you some results from both of those. But the other instruments that are aboard the spacecraft is that they're SWAP and PEPSI are fuels and particles instruments, which I know very little about. I'm not a fuels and particles person, so I'm not going to talk much about them. ALICE, which is a UV spectrometer. Again, I'm not going to talk too much about the results of the UV spectrometer. More interesting to me was the result of REX, which is our radio antenna. In fact, one of the people who work on that is a SETI employee. The REX instrument was used, amongst other things, do radio occultation of Pluto's atmosphere and get us more information about the structure of the atmosphere. Okay, here's the trajectory that we took. So as I say, we took off like a bat out of hell in 2006. 13 months later, we crossed the orbit of Jupiter, and we did have an encounter with the Jupiter system. We used it to both acquire some interesting new scientific results, which I think you've all heard me talk about in the past, as well as try out and test out and calibrate our instruments, which worked very successfully. Then a little more than 8 years later, we arrived at Pluto. At Pluto itself, Pluto has a spin axis which is somewhat inclined to the ecliptic plane, the plane in which all the planets travel in. And so the encounter was somewhat like coming onto a bullseye pattern at a 45-degree angle to the direction of travel. That had the unsettling effect when we planned the encounter of having most all the targets kind of all being near us all at once. So it was quite an exercise to put together the encounter so we could see a lot of Pluto, a lot of Charon, and capture some of these other objects as well, the smaller moons. But as you'll see, I think we were rather successful. Okay, so on to data. So here are the highest resolution global images taken from INVIC, the instrument I just mentioned ago, our wide-angle medium resolution camera. These images have resolutions of around 0.5 kilometer per pixel, a little better in this case, a little about that in this case. And in both cases, the color's been exaggerated. It's not, quote, false color. We've just taken the colors that are there and kind of turned up the tints so that you can see the variation in color. Using the same imaging system, the INVIC system, we looked back over our shoulder after we'd flown past Pluto to look at the atmosphere, and this is a true color view of the atmosphere. It turns out Pluto has a rather extended atmosphere that shows up very nicely. It actually is that bluish color. And when we look at it in detail, we took this picture soon after closest approach, and we looked back, and you can see this, if you could have seen this whole scene, this would be a huge crescent, right? And here you can see that the atmosphere is actually composed of a number of individual layers, and we think the individual layers are made up of essentially smog particles. There is methane mixed into a predominantly nitrogen atmosphere, and the methane is slowly converted into higher hydrocarbons, which turn into small particles. And so these particles are smaller than individual particles which make up cigarette smoke. They stay suspended in Pluto's atmosphere for some period of time, even though the atmosphere itself is very thin. As I said, the surface pressure we've determined from several means is around 11 microbars. 1 microbar is 1 millionth the Earth's atmospheric pressure. Okay, let's talk about some of the other results from INVIC and also the imaging spectrometer. So this cool psychedelic picture is actually created by principal components analysis of the individual color channels. And what it does show, in addition to just being a cool picture, is that these are actually showing the real color variations on the surface. So every different color represents something that's a different color from something else. They're not these colors, but it does show that there's lots of processes operating on the surface or in materials on the surface which cause it to have a range of different colors. And so what are some of those things that could be causing different colors? Well, let's look at the results from LISA, the imaging spectrometer. So first of all, there's methane ice. Methane ice shows up a lot of places. It's very common in the Arctic region. It's curiously very, very strong up on these ridges called the Tutares dorsae, which I'll show you pictures of them later on in the talk. And you also see it apparently coating the surfaces just above these cliffs in this region. I'll also show you in a moment. Here is the nitrogen ice. And the one thing I want to point out is this region called Sputnik Planum, which we'll be talking more about here very shortly. For a variety of reasons, we think Sputnik Planum is probably dominantly composed of nitrogen ice, but there's also a little bit of carbon monoxide ice in the system, and it turns out the only place you ever see carbon monoxide ice is the same place you see this big whopping signature for the nitrogen ice in Sputnik Planum. And undetected from the Earth, but detected by us, is water ice. So we see individual discrete spots where there seems to be quite a bit of water ice. There seems to be, you can make it out here in this image, there's water ice down here on this plain in front of this cliff system. And the dark regions also have water ice in them. And last but not least, you can see these big fracture systems, and there's a whopping water ice signature in those too. So we have two lines of evidence that the crust is dominantly made of water ice. First and foremost, we're seeing water ice when you look inside on the faces of cliffs, but also nitrogen ice and even methane ice to a lesser extent are simply too soft to support kilometers of topography. So when you see a multi-kilometer high cliff face, or a 2 or 3 kilometer high mountain, it has to be pretty much made of water ice. And so it's nice that both mechanically that's being demonstrated by simply seeing the relief, the topography, as well as seeing the signature of it in the spectra. Okay, so now I'm a geologist, so I'm going to talk about now for the next few slides about geology and how do we start doing geology. Well, step one is my colleagues and I, including Ross, we sat down and just began to see, does this landform look like that landform? Does that landform look like this landform? If they don't, then we identify them as separate landform and landform suites. If they look the same, we colored them of all the places we saw the same occurrence of the same type of landform. So as I I see that there is one small little glitch from going from putting your slides together on a Mac machine to a Windows machine that's got moved down. So it's a warning, this is not a geological map yet. This was just a landform identification map where we tried to identify the landforms. And another virtue of this process is that if you think you've identified everything, but you're still seeing bald spots on your map, that means that you still have more landforms to identify. So when the map is all colored, you identified all the landforms. That's basically how that works. Oops. So now this is a real geologic map. So we go to the next step where we actually, having recognized the initial suite of landforms, we use the technique of superposition. What seems to sit on top of something else, or our cross-cutting relationship is something is cutting some terrain but not cutting other terrains, to basically put things into a stratigraphic order where you can say what's on top, what's on bottom, what was formed early, what was formed late. And by this process, we actually begin to map out what are the individual geological units on a planet, in this case, the Sputnik Planum region. Sputnik Planum turns out to be a very highly complex region. Sputnik Planum itself is about the size of the state of Texas. We think it's mostly made of nitrogen with some unknown mixture of carbon monoxide ice. We think the ice is thick, and I'll show you some reasons why we think it's thick here in the next couple of slides. Okay, so on the surface of Sputnik Planum, we're seeing blisters, and we think these blisters are likely signatures of topographic uplift due to solid-state convection. As you heard me mention earlier, there is quite a bit of rock inside Pluto, so Pluto does mildly heat the interior, and we're dealing with these extremely cold, extremely volatile ices. The surface of Pluto is around 40 degrees K, which I think it's something like minus 400 degrees Fahrenheit or some absurd number like that. And so these ices are being mobilized, we think, by the gentle heating of the interior. And so much like when one stares into a pot of boiling oatmeal or something, we think these are just simply the rising and falling cells of this gently warmed, plastically deforming nitrogen ice. Nitrogen ice is very soft. The best metaphor I give most people for thinking about, or analog I give for thinking about nitrogen ice, it pretty much has the behavior at this scale in both time and space as silly putty. Okay, and mapping out weird things on the surface, we've just talked about the cellular terrain, which is more or less located here. There are interesting flow patterns, where things seem to be flowing up onto this higher surface here. I should tell you that what we think is going on with Sputnik Planum, we believe that Sputnik Planum itself sits inside a very ancient impact basin. It'd be the largest impact basin we have seen on Pluto, if it is indeed an impact basin. Because of its size, and basically by recognizing everything else seems to be superposed on this ancient impact basin or this topographic basin, whatever it is, that it's amongst the oldest recognizable things on Pluto. So it goes back to the very beginning of Pluto's history that this basin is there. But it seems to be a deep basin. I'll show you evidence for in a moment why we think it's deep. At the end of today's talk, I'll have you put your glasses on, and we'll look at things like the pitted plains here, which we think the pits are formed by sublimation process, which is sublimation is where ice directly evaporates in the same way that dry ice evaporates on the Earth. Okay, so here is the evidence that Sputnik Planum's nitrogen ice is deep. This is a topographic map where we took images taken at different times during the encounter to give a stereo perspective, which is, of course, the images you'll be seeing at the end of the talk. And by knowing precisely where the spacecraft and cameras were, when the pictures were taken, we can then use trigonometry, basically, to derive the elevations. So these big blocks that are setting out here along the inside, but along the edge of Sputnik Planum, stand several kilometers above the plane of Sputnik Planum itself. And so it's an interesting property of nitrogen that nitrogen is less dense than water ice. Nitrogen ice is less dense than water ice. It has about the same density contrast that liquid water has to solid water. So as a consequence, blocks several kilometers high, and we think they're water because, as I said, they would be able to support that kind of topography, are essentially being rafted or even floating in a deep deposit of softly deforming lower density nitrogen ice. And we think that, for instance, perhaps these blocks may have begun originally attached to the rim here, but simply drifted out into the interior as nitrogen ice levels may have risen and fallen over the history of Pluto. I'll show you evidence that things are both being fed into Sputnik Planum as well as perhaps sublimating out of Sputnik Planum. Let me see if there's anything on these talking points that I haven't already mentioned. I think that pretty much covers what I just said. It is interesting to think that even the largest mountains on Pluto could just be floating in a deep deposit of nitrogen ice. I showed you in a couple of slides back where there was evidence that the nitrogen ice was kind of pushing up against the shore in the northern part of the image. Down in the southern part of Sputnik Planum, we have evidence of glacial flow. So here you can see B shows these two little valleys where nitrogen ice, which has been deposited up here on this higher topography, has been sliding down, like I say, think of silly putty, through these valleys and is forming lobate deposits out on Sputnik Planum. In fact, this region right here where it's coming out is seen with different lighting, where the streamline of material that's coming down into the valley can be better seen. So we think we have good evidence that we're seeing some glacial flow filling in Sputnik Planum at this location. And the glaciers are, of course, nitrogen. Well, before we completely leave the Sputnik Planum region, I should mention we see some very weird mountains on Pluto. We were reticent to run off and say we saw ice volcanoes because there's a lot of reasons to be be skeptical that the icy worlds can really produce this kind of volcanism. But here you have them. Right Mons, which is this feature here, is 3 or 4 kilometers high. It has a 5-kilometer deep pit in the center. If you look at these objects, they have, why not working out? Oh, it's just because it's green, I see. There's these weird, pillowy constructional textures. It's really hard to explain how these two mountains could have formed through erosive processes. So I think we're left with the idea that they're formed by some kind of constructional process, perhaps a form of so-called cryovolcanism, which is a fancy word meaning ice volcanism, or in conjunction with some additional tectonic activity. So we haven't seen them erupting, but there they are, and if they do indeed turn out to be cryovolcanic features, then they are almost unique in the solar system, because the other things we've seen in the solar system, which either are erupting, like on Saturn's moon Enceladus, or landforms we see elsewhere, such as on Triton or Ganymede, they form very low flat-lying areas. They don't usually produce high standing relief. And again, because they're high standing relief, they almost certainly have to be made of water ice. So that is even more difficult to understand. It's one thing to invoke the gentle radiogenic heating of the interior to mobilize nitrogen ice, which is, as I say, soft and very volatile. But it's quite another to invoke sufficient warming to actually mobilize water ice and make it produce these mountains. So we're still being cautious about truly identifying them as volcanoes. Here are some other processes formed by interior processes, so-called endogenic processes, tectonics. Clearly, here's a huge fracture system. This fracture system is 4 kilometers high. This is the same fracture system. I said we were able to look into the cliffside face and see water ice. The fact that it's so high means that we already could guess that much of the crust had to be made of basically water underneath the veneer of more volatile ices. You can clearly see that the fracture cuts this crater, so we know the fracture formed after the crater did. So a combination of things, the fact that the fracture systems have different orientations and they seem to be at different ages and different states of degradation suggests that Pluto has, throughout much of its geologic life, had processes operating which caused the surface to be active and be fractured. It's kind of a take-home message from that. I mentioned the idea of nitrogen glaciers. Well, a lot of the upland terrains of Pluto are carved into these dendritic valley patterns. And we think the dendritic valley patterns, in fact, are formed by the flow of nitrogen-rich ice, perhaps accompanied by basal melting down at the very bottom of the ice flow. And we think it involves accumulation of ice, glacial flow, and erosion. And we think this is the dominant mechanism that forms a glacial erosion on the Earth. So we think that what we're looking at are vast landscapes shaped by glacial erosion of nitrogen glaciers. There are two possible explanations for how this widespread landscape has been formed. One would be the idea that in the past, Pluto had much thicker ice sheets up on the surface, and these ice sheets have slowly been moving into low-lying areas such as Sputnik, Planum, and also they've been slowly sublimating away, so that over the lifetime of Pluto, Pluto may have lost a lot of its nitrogen, so we're just kind of seeing the whole system run down. And so in that case, this would be a metaphor similar to the thick ice sheets you see streaming at the margins of terrestrial plateaus, such as Greenland and Antarctica. The alternative is, and these are not mutually exclusive, both processes could be happening, the sublimation of nitrogen off the surface of places like Sputnik, Planum could be reprecipitating back on the highlands, and you could essentially have the equivalent of a hydrological cycle where nitrogen collects back on the surface and flows back down in Sputnik, Planum. This process could be repeating. So, and that's more of a model that's similar to things you see that form alpine glacial flows, such as the glaciers which have historically occupied, for instance, the Rocky Mountains and the Sierra Nevada. Speaking of sublimation, we see evidence for scarp retreat. So here's a large scarp that's several hundred meters high. As I showed you earlier in the images of the spectroscopic data, there seems to be a lot of methane ice that's accumulated up here on the above the scarps, up on the plateau above the cliffs, and there seems to be a lot of water, a signature for water down on the surface. So we think what may be happening is that methane, which is less volatile than nitrogen, but still nevertheless volatile enough, may be subliming away. It may have been mixed intimately with water ice as the methane sublimes away. You are left behind with a much lower plane out in front of the scarps, which might be covered with the rubble or the detritus left behind of water after the process evolved. Now, there are several things that we have to consider. Methane, we're not quite sure how strong it is. There's at least two major studies. One suggests that methane ice is strong enough to hold up several hundred meters of relief, but other studies suggest it may not be much stronger than nitrogen. So I'll show you this image and the next image, features which seem to significantly involve methane ice. But the methane ice, if these things are truly made of methane ice, so this is the so-called bladed terrain, then the methane ice must have the ability to support several hundred meters of relief because these things are several hundred meters high. So what we're looking at here is the other scene I showed you earlier where we have a very strong methane signature. We're not quite sure what forms the so-called bladed terrain. It perhaps could be, we think sublimation plays a role, but we're not sure. We aren't looking at a surface that may have simply been pushed up tectonically and fractured, and the fractures are simply being widened by sublimation. Or alternatively, it could be a precipitation process that basically methane likes its high standing topography and is simply accumulating there to form ridges of precipitated methane ice. So we're still trying to understand that. As I said, we didn't see any nitrogen with the bladed terrain. Nitrogen is, at any rate, too soft to support it. So again, we support the idea it might be methane, but the jury's still out whether methane is actually mechanically strong enough to support it or not. Also up in the Arctic, we see these really deep pits. These pits are typically 3 kilometers deep. We're not quite sure what forms them. We think there could be a local removal of upland terrain by sublimation. We also see these deposits down on the floor here, as this bullet alludes to, which are either a material that's precipitating out of the atmosphere and accumulating on the floor, or alternatively it could be more evidence of so-called cryovolcanism flowing up and basically eating away at the scarps as the stuff flows out. We're still very open to which one of those they are. But it performs a very interesting province. As you can tell from many of the things I'm saying, we're still right in the middle of analyzing the results, and rather than give you definitive and probably wrong explanations, I'm simply going to continue to show you that, if you feel confused, so do we. We're still working the problem. The crater statistics are interesting. There is on Pluto a range of ages from very heavily cratered terrains, which must date back to the beginning of solar system history, to places like Sputnik, Planum, which show no craters whatsoever on their surface. And so, at least with respect to crater retention age, they're essentially modern. They could have formed a week ago, for all we know. And in fact, all plausible models for the rate in which craters form on the surface of Pluto suggest that if you look at a place the size of Texas that has no craters on it, it certainly can't be any older than about 10 million years old, and probably much younger. But again, since Sputnik Planum seems to be a big deposit of nitrogen ice is soft, we're not surprised you don't see any craters on it. They just basically melt away again, think about the silly putty metaphor. Charon, which I'll show you in a moment, has a younger plains unit, which you will see, but again, it's cratered enough that it's only relatively young. It's probably approaching 4 billion years old. And I'll remind you that the Mare, the dark lava plains of the moon, are typically around 4 to 3.5 billion years old, even though they have far fewer craters on them than the lunar highlands. So probably something similar to that is taking place on Charon. One really interesting thing that came out of our crater statistics analysis was that there seemed to be a paucity of small impactors, that we expected there to be your typical power law distribution of impactors, that there would be far, far more smaller impactors than larger impactors, but there seems to be a roll-off in the Kuiper Belt where there doesn't seem to be a lot of smaller and smaller, ever increasingly smaller objects. And The other evidence we had for that was when we began to conduct our search for our KBO target to fly to next, that we were having a hard time finding smaller objects, and finally had to use the Hubble telescope to find our next target. And that was also a clue that people's expectations of really small objects in the Kuiper Belt have not been met, that something operates in the Kuiper Belt to prevent the formation of these small objects, or else they've been swept out, which is an alternative explanation. So let's talk about Charon. Charon, as I said, is half the size of Pluto. It's about 1,200 kilometers across. The north half of it is cratered and broken up by these big tectonic fracture zones, these rift zones. And the southern half of it, as seen from the spacecraft, is made of this much smoother plains. And you see we've been using whimsical names for all of these. In fact, all the names you've heard me use today are unofficial names. We didn't want to keep on calling it Crater A and Plain B, so we gave them names. And so, as I said, their names simply being used within the team, although I want to recognize our Mark Showalter's here in the audience, who ran our very major project through the SETI Institute to come up through public involvement with names that we've given the features on Pluto and Charon. And so we've given them names which I think may well stand the test of time. We'll simply have to see. So as I said, the plains unit is smoother and somewhat younger, but still relatively ancient. Well, let's look at the plains unit a little more closely. You can see it is more or less flat. Here's again another topographic high-resolution stretch of images, or swath of images we took across the plain. We have colorized with topographic information. And so the warm colors are high and the cool colors are low, and changing in color means the topography is coming up and down. And you see a lot of things on the plains of Charon and Vulcan Planum, which remind you of the things you see on the moon's mare, or lava plains. You see these fracture systems at sea, which for whatever reason I have a hard time getting it to show up on the. I may have to give up on that. Well, it's at sea. You can see there are these rill-like systems, which are probably tectonic fractures. D shows where there seems to be a small pancake-like feature, which might be formed by the eruption of material on the surface. Up here at B, Kubrick Mons, is a very large mountain block. It's a few kilometers high, and it's completely surrounded by a moat. And then you can also see further up here at A, there are big depressions where you have look like lobate surfaces flowing into the depression, but there isn't a mountain in the interior. And we suspect, and you can also see along the periphery of Sputnik Planum, it can be seen here in this I'm giving up, it's not showing. The edge of Sputnik Planum, where it comes up against the highlands topography, also seems to be dipping downwards. And all this may suggest that Sputnik Planum isn't placed as a viscous cryovolcanic lava flow, but it's viscous enough that it's retaining a lot of its topography, isn't simply filling in things like the way, for instance, Sputnik Planum just fills in the basin in which it occurs, because it's made of much softer material. Well, here are about the best images we took of the 4 smaller satellites, and hopefully Mark will be invited to give a talk sometime about this, because this is really his specialty. He contributed substantially to the New Horizons science team by helping us understand the population of these things, the possible risk that ones which we didn't see, fortunately, could have posed to spacecraft, and so on. And see, we kind of had 2 big ones. The ones that were discovered earlier were Nix and Hydra. And then we discovered Kerberos and Styx somewhat later in the game. Nix was the one we could actually get close enough to show some more detail. So we got a color image of Nix you can see on the lower left. And then this last image is Nix close up. It has the resolution of around 300 meters per pixel. And now the resolution is good enough that you can see that there are, for instance, fracture systems running across the surface. So I'm going to end this part of the talk by showing you this intriguing painting, which looks like some artist painted a view of Sputnik Planum from the highlands, but this painting is in fact done in 1961 by the famous mid-20th century space artist Chesley Bonestell. I always wonder how Chesley always knew so much. He died in 1986, but I just like to show you that because it's cool that people thinking about what little they did know about Pluto in the 1960s, that they could imagine something like this and not be too far from wrong. Okay, so stay tuned for our next encounter, which will be on New Year's Day of 2019. We'll fly past our Kuiper Belt object. And I think the next...
all the Pluto data downloaded by then.
Well, yeah, working on it. We should have most of it down by the end of the year. And most of the stuff that I've shown you, obviously, is already down and by definition. And most of the imaging that have resolutions of better than a kilometer per pixel, except for one or two frames, we pretty much got brought down already. So the geologists have skimmed off the early downlink to take advantage of being able to show people like ourselves and you guys the cool pictures that we've taken. Okay, and that's now everybody can, we may also need to bring down the house. What should we start with? Let's start with this one. Okay, so this is along the edge of Sputnik Planum.
Turn the lights down?
Yeah, let's turn the lights down a little. If we can, if that's an option. So Sputnik Planum, you can see, is the smooth surface that's along the top of these images. And just beyond it to the west, so north is to the left, is this much darker and heavily cratered region, which we call Cthulhu Regio. And here you can see very clearly how the material apparently has sloughed off into Sputnik Planum and forms these blocks of material that you see setting out along the edges of Sputnik Planum. And as we pan along here, you can see that Sputnik Planum itself is very smooth. Here's some Sputnik Planum material, nitrogen ice, embaying and filling in a crater. And as we come up towards the end here, you can now see right Mons, our possible volcanic feature, coming into view. Let me see if we can make it a little bit bigger. Cool, huh? And so you see a lot of these other blocks are sort of setting out around the area, such as these features right here, may well just be blocks of material, for all intents and purposes, floating as water ice detritus in a deep deposit of nitrogen ice. Everybody's had a chance to absorb that. We'll go on to the next image. You're all ready for the next image? Okay. Let's try. Okay, here's a view of the Highlands unit just north of Sputnik Planum. And as you can see, it's what you would expect. You can see this is just a cratered surface. You can see very deep craters formed in the largely water ice crust. And as you move towards Sputnik Planum, you can see these very deep valley systems, valley networks. So these are the valley networks we think that have been carved by nitrogen glaciers, and they do look very much like, nitrogen carved valleys you can see up in the Sierra Nevada. I do need to tell all of you that the relief has been exaggerated substantially, like a factor of 20 to 1, so things are not as steep looking as they are in these images. It makes it very easy for you to see what's up and down, but the relief is a little more subtle than that. To put things in perspective, this scene's probably, 30 or 50 kilometers across, and topographic relief here is only maybe 2 or 3 kilometers. So as we move on, I'm going to go to the next image, as you'll overlap this scene as we go on to Sputnik Planum itself. So here's those glacial valleys again. And here you can see kind of an abrupt break and what looks like loose detritus material that seems to be sitting or floating, for lack of a better term, off the edge. And then here are all these big blocks I showed you earlier that are on order of 3 or 4 kilometers high that we think are rafted or floating in Sputnik Planum. And once you get past the blocks and get into Sputnik Planum itself, you can see it's flat. And so just the chaotic nature of these blocks. In fact, the chaotic nature of the blocks is reminiscent of chaotic terrain or chaos terrain on Europa. And although exactly what's floating and what is different between Europa and Pluto, it's interesting that they have such similarities in the relationship between the material which makes up the chaotic terrain and the material in which it floats. And last but not least, here is the highest resolution images we took. These images have a resolution of between 70 and 80 meters per pixel. And here we are out on Sputnik Planum. Curiously, this portion of Sputnik Planum seems to be covered by these pits, some of which form strings of pits, which we've informally referred to as bacilli, because they look like bacteria colonies under a microscope. And as you can see, the surface is very flat, as you would expect. These textures, including the so-called bacilli, we think are entirely due to sublimation. We think the sublimation pits of nitrogen ice evaporating directly into the thin atmosphere of Pluto. Pluto's atmosphere is in pressure equilibrium with the nitrogen sublimation rate explains why Pluto has the atmospheric surface pressure it has. It's in equilibrium with the escape rate of nitrogen due to sublimation. Interesting, as you get closer to the end of Sputnik Planum, you get into these very strange, huge pits. We think they may well have formed by sublimation or something like that, but honestly, we're still trying to figure out, what's going on here. And so I will leave the formal presentation with the fact that Pluto's turned out to be much, much stranger and much more amazing than any of us really realized before we got there. And as you can see, we're still frankly scratching our heads and trying to figure out what the heck's going on there. So with that, I'll end my presentation and take some questions.
And while you're all formulating your questions to ask Jeff, as a token of our esteem, the SETI Institute will present you with our very handsome SETI Talks mug for you to remember your talk here today.
Thank you.
So if you have questions, please raise your hand. Yeah, in the back.
Yeah, what was the KDL object that is the next target? Does it have a name?
It has a name which I can't remember, like RU61 or what is it?
Close. It's MU69.
We're going to give it a better name soon, but
Yeah, Bill.
You mentioned nitrogen ice. Is there any evidence for something like argon as well?
Well, we looked for evidence of it. Unfortunately, argon doesn't have much of a spectral signature. We didn't see any. In fact, we were more anticipating we might see some oxygen ice based upon the detection of oxygen at the Rosetta Comet, but we haven't seen that either, and we've looked very carefully for oxygen. Another material we would have liked to have seen or thought we might see was carbon dioxide, but we haven't seen any CO2 either.
Okay, you said there was maybe a small layer of liquid water. There's
Solid.
some heating from the interior. Is this? It seems too small to be radioactive planet. Or could it be tidal heating?
No, the tidal heating won't work. There's no because it's just two bodies. There isn't tidal heating. But they're in circular orbits about each other, so they're locked. There's no mechanism there for tidal heating.
So it needs to be radioactive heating?
Yeah, I mean, silicate rock has, probably, potassium, uranium, and thorium in abundances comparable to, say, the crust of the Earth. And so it's a reasonable assumption that there is, enough material which is slowly undergoing radioactive decay, which would gently heat the interior. And there's various arguments which are long to go in to why one might think there's a small liquid layer sitting above the rocky mantle and several hundred kilometers beneath the outer icy upper mantle and crust.
All right, I'm reminded that we're being recorded, so I have a microphone here. If you have questions, let me get it to you. Questions? Yeah, in the back here? Let me get it back here. Now I have to run around with the microphone.
Was it significant that there was water ice discovered, and what would they do with that information?
Well, the significance of it is we didn't see water ice in spectroscopic studies from Earth-based telescopes or from the Hubble we'd never seen water ice detected unambiguously on Pluto prior to the encounter. And had we arrived at Pluto and seen no evidence for water ice either in high-standing topography or a spectroscopic signature, it would have implied that the crust might have been many kilometers thick, may have had a many kilometer thick crust of nitrogen or methane or some softer, more volatile ice. But as we can see, the methane and nitrogen occur in specific locations, and elsewhere, the steep cliffs, the floating blocks of material, the signature of water ice itself, it tells us that, at the 10-kilometer scale, the crust of Pluto is dominated by water ice, and these other materials, nitrogen, methane, are local materials which accumulate regionally in the same way water accumulates in ocean basins on the Earth.
Since Pluto's orbit is famously elliptical compared to the 8 major planets, can you speculate as to how it might look different if we flew by at a different time in terms of sublimation or because of the different temperatures, that sort of thing?
Well, right. It has extreme seasons over its 200 some odd year long Pluto year, and one would anticipate that there are seasonal changes on Pluto, and we see indirect evidence that on larger timescales there are million-year precessional cycles on Pluto, and we think that may contribute to where particularly the nitrogen ice may accumulate and then may be transported to other parts of Pluto. So the so-called hydrological cycle I alluded to is one of the hypotheses we're considering for how nitrogen may move in and out of Sputnik Planum. Could be driven by either the seasons of Pluto or perhaps the Malekhovich cycle scale mega seasons of Pluto. So yes, you're right. If we pass a different time, we probably see something else going on. And Pluto seems also to be a very heterogeneous world that I suspect that just what we saw is not necessarily being just replicated elsewhere on Pluto. If we could have seen the whole world, I imagine we would have seen interesting processes and landforms which we didn't see with this encounter. We saw about 40% of Pluto with this encounter at resolutions sufficient to have a meaningful conversation about the landscape.
So you said that Pluto had a small atmosphere?
Yes.
And I'm wondering, so is there any evidence of any storm activity going on? And if so, could those little pockmarks be maybe giant hail or something like that? Or is that pretty outrageous?
The atmosphere is just too thin. It's about 1/100,000th as thick as the Earth's atmosphere. And so there isn't any real sensible weather in the sense that we would think of convective weather on the Earth. It's perfectly possible that it could have some very thin but strong directional winds, which might contribute to the orientation of sublimation features. We're investigating that as a possibility, but we don't think anything except nitrogen ice and to a lesser extent methane ice precipitates out of the atmosphere. And in that case, it doesn't so much snow as it just gets cold and frost up.
Hey, Jeff. Thanks for the talk. It was really cool. When you were showing us these images, the stereo images, the first one you showed us on the far right, you had your donut-shaped volcanic construct, whose name I forget. I don't know if you care to go back to that image, but all the terrain to the left of it was actually low-lying, and that's what gave the donut shape. But the stuff to the right just seemed to be at the same height as the construct itself.
Well, the picture shows you both Right Mons and the volcano we see just south of it. They are next to each other, as they were shown in the slide maybe halfway through the talk. The other volcano we don't see in direct sunlight. We're only able to see it because those layers of material which are suspended in the atmosphere scatter sunlight into the near darkness just beyond the terminator. And so we're seeing the rest of that portion of Pluto from scattered light. So they are basically next to each other, and that whole surface is quite topographically rough. And even though Right Mons and Picard Mons, which is the Mons just south of it, do stand out as discrete rises with central depressions, they are in a terrain which is itself mountainous. And so that's why I've hemmed and hawed about whether it's strictly volcanism or volcanism with some combination of tectonism or some kind of weird tectonism which I don't understand, which is perfectly possible.
Is there any evidence of a magnetosphere, and is the atmosphere being stripped off to any extent?
There is no evidence for a magnetosphere. We did not fly a magnetometer, but the two fields and particles instruments showed the behavior of the solar wind and the loss of the atmosphere around Pluto consistent with no magnetic field to speak of. And the atmosphere is being stripped off. It's actually being stripped off at a much slower rate than the model suggested it would be stripped off at this time. But what does that mean for long-term retention of the atmosphere and replenishing of the atmosphere? We're still trying to understand that. It was a surprising result that it's being lost at a rate of about 1/5 what we thought it would be lost at. But that's, of course, a snapshot in time. What does that mean during other times in Pluto's orbit when it's closer to the sun, or for that matter, what does it mean over millions of years? We don't know.
Jeff, it's been a wonderful talk, but I wonder when you show us some of these characteristics, the structures, in particular the fact that it's very cold, you have all these different ices. Water ice, of course, has a lot of different phases.
Yes.
And so what we're seeing, of course, is a release of several kilometers, so very high pressures at the basis of some of these things. So do you think that the phases of the water ice and nitrogen ice and methane ice play any role in the complexity of the structures you're showing us?
Well, maybe so with nitrogen ice, because nitrogen ice, it's two different major phases, so-called alpha and beta nitrogen ice, occur at pressures and temperatures which are in the range of Pluto's surface temperature, and also you would have to go very far down because of the nature of nitrogen and being a very volatile material, that it both would change ice phase, and if you go down more than a few kilometers, it may even have basal melting. So nitrogen probably is the most interesting player in this as far as phase changes. Water ice, again, the gravitational forces on Pluto are small. They're about half that of the Earth's moon. You have to go very far down in pressure to go from, say, ice 1 to ice 2 or 3. So probably there aren't any significant ice phases involving water ice. I guess reprecipitated water ice might be amorphous initially, but I would think it would pretty rapidly crystallize into ordinary, ice 1 crystallization. That's what we anticipate we're looking at. And in fact, if Pluto indeed does have a liquid water layer at the base of its ice shell, we think it's probably going directly from ice 1 to this liquid water state. And Francis Nemo, a colleague of ours at UCSC, I think many of you may know him, has seen some indirect evidence there may indeed be this ice water layer, H2O layer, liquid layer at the base of the ice shell, but that's still work in progress.
Did you get any images of Charon? And if so, is the topography different?
Yes, I showed you some images of Charon.
Okay, I didn't see those.
Okay. Oh, 3D ones. So we do have some 3D ones, but I don't have them with me, I'm sorry to say. Although you could tell we obviously had such data because I showed you the view of Sputnik Planum. It was colorized with topographic information, which was derived from our 3D coverage of Charon.
Well, we've kept you past 1 o'clock. Jeff will still be here to answer questions if you like. But other than that, thank you for joining us today at the SETI Talk.
Thank you.